It's a great pleasure to introduce Monica Clapp, my dear friend, for this last talk of this session. And Monica, it's a great pleasure to see you.
It's a great pleasure to see and to kind of feel all of you in this spirit. So, okay, so hi everyone. Let me first say that, I mean, it has been very refreshing to listen to beautiful mathematics, especially in these very strange times that we are all living. So thank you, Angela. Thank you, Susanna. Thank you, Hugo, for organizing this meeting. So I am going to be speaking on joint work with all of these guys, not with all of them together. So some results are with Andre, other results are with Andre and Alberto, and then I will speak also on some ongoing work with Angela. So the starting point is the Yamabe equation. So the Yamabe equation is this equation right here on a manifold M. So I will assume that M is a closed Riemannian manifold of dimension larger than or equal to 3. And little m is going to be the dimension of the manifold. So this capital SG is its scalar curvature. And the operator here is the conformal Laplacian, which is made by the sum of minus the Laplace-Beltrami operator, which is this operator right here, and then a multiple of the scalar curvature, which, and this multiple depends only on little m, which is the dimension of the manifold M. And on the right-hand side, the exponent is the critical Sobolev exponent in dimension M. So I will assume throughout that the conformal Laplacian is coercive. That means that the quadratic form induced by the conformal Laplacian is coercive. So this is the same as saying that the Yamabe invariant, which is this guy defined right here, is strictly positive. Okay, so the problem we want to address in this talk is the existence of optimal partitions for the Yamabe equation. So what's an optimal partition? Well, an optimal partition is you choose a number L larger than or equal to 2, and then an optimal partition consists of L open subsets of M, which are non-empty, pairwise disjoint, and satisfy the following two conditions. The first condition is there should exist a solution for the Yamabe equation on the domain omega I with Dirichlet boundary condition, and it should have a minimal energy. This means this solution should be a minimizer for this Yamabe quotient on omega I, and I will call this infimum y omega I will call it the Yamabe invariant on the domain omega. So that's the first condition, the existence of a minimizing solution to the Yamabe equation in omega I. And the second condition is that the sum of the Yamabe invariants for the omega i's should be less than or equal to the sum of the Yamabe invariants for any other collection of sets in the partition. So the question that we want to address is whether there exists an optimal L partition for every number L larger than or equal to 2. And the answer is no. So if you take, for example, the standard sphere, the M sphere, this does not admit an optimal L partition for any L. And the reason is very simple. So let me show you that. So you see the Yamabe equation is conformally invariant. This means if you replace M by any manifold which is conformally equivalent to it, then you get an equivalent equation. So since we are talking about the sphere, we can take the stereographic projection and transform the Yamabe equation to somebody has a question? Or?
Sì, Luca Battaglia has a question. Sorry.
Ah, okay. Where do I see the question?
Luca, do you want to ask the question? No.
I think he exited the room, maybe by accident.
Okay, okay. Sorry.
So then we have the stereographic projection, and the stereographic projection transforms the Yamabe equation on the sphere to this other equation, which is very well known to all of us. And what is the Yamabe invariant? Well, the Yamabe invariant is nothing else but the best Sobolev constant for the embedding of the Sobolev space into L2 star. I will be using the letter sigma for the this best Sobolev constant because I have already used capital S for the scalar curvature. So sigma is the best Sobolev constant, which is the Yamabe invariant on the sphere or in Rn. Now, as we all know, this infimum is attained by the standard bubble and by any translation and dilation of it. So this means that we may translate the standard bubble to center it in a point inside any domain, omega, and then dilate it as much as we want. And what remains outside is negligible. So this quotient now only on the domain omega is again the best Sobolev constant. So this means this quotient cannot be attained, because if it were attained, then the quotient on the whole space would be attained, and that would be a solution which is trivial outside the domain, and this is impossible due to the maximum principle. Okay, so this is telling us there is no optimal partition for the Yamabe equation on the standard sphere. Okay, so the question remains: what happens if we take an arbitrary manifold different from the standard sphere? So to study this question, what we are going to do is we are going to follow the approach of Conti, Terracini, and Berzini. So we are going to consider a weakly coupled system related to the Yamabe equation. So this is a system similar to the system that was considered by Thomas in his talk, only that now here we have the conformal Laplacian. Here we have the critical Sobolev exponent, and the exponent of the interacting term I will take to be half the critical exponent. So the idea is that all of the summands have to have the same exponent. Okay, now here the lambdas, the notation is different from the notation that was used by Thomas. So the lambdas are the coefficients of the interaction terms, and these lambdas will be assumed to be negative. So the idea is to, well, okay. So as Thomas mentioned also, this system may have solutions whose components are trivial. We are not interested in those solutions. We are interested in fully non-trivial solutions. This means solutions where all components are different from zero. So we are going to look for these solutions. And so the question is whether the system has a least energy fully non-trivial solution. That's the first question. And then we want to look at the behavior of the solutions, if they exist, as the lambdas go to minus infinity. And we hope that the behavior, I mean, it is well known that the components separate in space as the lambdas go to minus infinity. So we want to see whether this gives rise to an optimal partition. So this is precisely following the same program as Conti, Terracini, and Berzini. Okay, so what is the variational setting? Well, we have to take the Sobolev space on the manifold. So this is just the Sobolev space of L2 functions, which have L2 weak derivatives on M. And since we are assuming that the conformal Laplacian is coercive, we may take this guy as the norm in the Sobolev space. And then we have we can look at the product of L copies of the Sobolev space and at the functional, which is given by this expression right here. Okay, so this functional is of class C1. Its partial derivatives are given by this expression. So when one looks at this expression, one clearly sees that the critical points of the functional J are precisely the solutions to the system. Okay, so now let us, we want to look not just for any solutions, we want solutions which are fully non-trivial. So we are looking for solutions which belong to the set, which I will call N, which have components, all components are different from 0, and the partial derivative in the direction of each of the components is equal to 0. Okay, so now we look at the functional and we look at the infimum of the functional on this set N. And as it turns out, this set N is very nice in our case. So since the lambdas are all negative, one has that this set N is indeed a closed subset of the product of the Sobolev spaces. Also, this guy, the infimum, is bounded below by an expression which involves the Yamabe invariant. And since the Yamabe invariant is positive, so this is bounded below by a positive constant. And then the third property, which is the one which is interesting for us, is that if you find a minimizer on this Nehari set N for the functional J, then this will be a fully non-trivial solution to the system. So the question is whether this guy, this infimum is attained or not. Okay. So what we proved together with Angela is the following. We proved that if the manifold M is not locally conformally flat, and if the dimension of the manifold is larger than or equal to 9, then indeed this infimum is attained. So the Yamabe system has a least energy, fully non-trivial solution. Okay? Now, to prove this, of course, we need some compactness because the critical exponent is there. So there is, in general, no compactness. So we need a compactness criterion. And then in order to check the compactness criterion, what we need is an appropriate test function. Okay, so let me just give you a sketch of how this goes. Okay, so we are going to look at subsystems of the system. So we look at a set of indices C between 1 and L. And what we do is we erase from our original system all components whose index is in the set C. So then we have a system with less equations, with L minus the cardinality of C equations, and we look at the corresponding infima. And then the compactness criterion says, well, the infimum of the original system, for the original system, is attained if it is smaller than all of these numbers, which are the infima corresponding to the set of indices Z. And then we complete by putting here the energy of the least energy of the Yamabe equation on the sphere. Okay? And in fact, I mean, if you take only one equation, if you don't have a system, you just have the L equal 1, so then you have the Yamabe equation, then this reduces to the condition that was given by Aubin. So the condition of Aubin says, if the Yamabe invariant of the manifold is strictly smaller than the Yamabe invariant of the sphere, then there is a solution to the Yamabe equation, a least energy solution to the Yamabe equation. So this proposition just generalizes the criterion given by Aubin. And now we want to check whether this condition, this strict inequality is true. So for that, we need a test function. And so this test function works well if under these assumptions that M is not locally conformally flat and has dimension larger than or equal M. So what is the test function? Well, we construct it inductively. So then we take a system with L-1 equations. We take a solution for the system, a minimizer for the system of L-1 equations, and we complete by taking the test function that is used for the Yamabe problem. So first we have to choose a point in the manifold M for which the Weil tensor is non-trivial. This we can do under the assumptions that we are considering. And then we take the test function introduced by Lee and Parker for proving the Yamabe conjecture. And well, the candidate for a test function would be, well, you take the first components, the first L-1 components to be the solution for the system with L-1 equations, and then the last component should be the test function of Lee and Parker. Now, this is not necessarily in the set L, in the set N, in the Nehari set, but one can multiply, one can project it onto the set N just by choosing suitable constants, SI, positive numbers, and multiplying the components by these numbers. So now we use delicate estimates that were computed by Esposito, Pistoia, Vetois for the Lee and Parker test function, and using these energy estimates, we see that under the assumptions that we are considering up here, so if M is not locally conformally flat and the dimension is larger than or equal to 9, then indeed the energy of this guy is smaller than this number. And so this proves the existence of a fully non-trivial solution for the Yamabe system on the manifold M if M satisfies these assumptions. Now, let me say that, well, the sphere, of course, does not satisfy these assumptions because the sphere is locally conformally flat. And in fact, the Yamabe system does not have a least energy solution, a fully non-trivial solution on the standard sphere. So there are exceptions for the existence, and the exception is given by the sphere. So now I would like to look at the question whether, I mean, before looking for at the behavior of these least energy solutions that we obtained with Angela, let me take a closer look at the sphere, okay? So the Yamabe system does not have a least energy fully non-trivial solution. We know that there are no optimal partitions on the sphere, but let us take a closer look at the system. I mean, the reason why one does not have a partition on the sphere is because, I mean, there is no compactness, and because we have this invariance under dilation. So let us try to put some compactness inside the sphere by considering symmetries.
May I just ask a quick question? I'm Hugo. Hi.
Yes.
This is for the competitive system, or it never
This is
has
only
to?
for the competitive system because I am interested in partitions. So I am. So the lambdas, the coefficients of the interaction terms will always be negative.
Okay.
So then this Yamabe, this Nehari set is a nice set. Okay. Okay. So now we are going to look at the problem with symmetries. Let us put in some symmetries into the game. Okay. So we are going to look, I mean, the sphere it has a lot of symmetries, and this means that, okay, so we are going to look at a group of linear isometries in Rm+1. So the sphere is contained in Rm+1, and this group acts by isometries on the sphere. Okay, the sphere is invariant on in fact, this is the group of isometries of the M sphere. And now we want to translate the problem into Rm, because we are more familiar with equations on Euclidean space. So let us just translate this group action to Rm. So how does this go? Well, we take a transformation gamma, which is a linear isometry of Rm+1, so one dimension higher. And now we want to see how this guy gamma acts on Rm. So we take a point in Rm, we take it back to the sphere by using the inverse of the stereographic projection. Then we apply gamma -1 to this point, so we get another point here on the sphere, and then we bring it back to Rm by taking the stereographic projection. So you take the composition of the inverse of the stereographic projection, and then this gamma -1, and then the stereographic projection, and this gives you a conformal diffeomorphism. So this action is not linear anymore. This is a conformal action, okay? And since the Yamabe equation is conformally invariant, so this kind of conformal diffeomorphisms work well. So now let us why do we take these groups? Well, we take these groups because they have very beautiful subgroups. So let us take a subgroup gamma, which is the product of the group of linear isometries in k variables times the linear isometries in n variables, where k plus n is the dimension of the space m+1. Okay. Now, if we take the subgroup, the nice thing about it is that if we look at the orbits under the action of this group, so the orbit of a point, you take a point in Rn, and the orbit is just apply all of the conformal transformations that I defined in the previous slide for every gamma in capital gamma, okay? So what are the orbits? Well, the orbits are either a sphere in dimension k-1, or a copy of Rn-1, or a product of a sphere k-1 times k dimension n-1. So here is a picture in dimension 3. So if m+1, if m is equal to 3, then I am taking k and n to be equal to 2. And you can see the orbits here. So then you have k is equal to 2, so here you have a circle. And what's the circle? Well, this is just the unit circle sitting in the xy plane in R3. You have another orbit, n is equal to 2, so this is just a copy of the real line, and that is just the z-axis. And then the other orbits are S1 times S1, so they are tori. So this is a picture of the orbits, which are not linear, I mean they are conformal, in R3, okay? So the nice thing about this action is that, you see, if you take k and n larger than or equal to 2, then every orbit is a manifold of positive dimension. So there are no orbits that consist only of points or of a single point. Every orbit is a manifold of positive dimension. So now if you look for solutions which are gamma invariant, that means if you look at functions which are constant on each one of these orbits, they cannot blow up, because blow up for the critical exponent occurs only at points. It cannot occur at something which has positive dimension. So this means if we take a domain omega, an open set, which is now gamma invariant in Rm, and we look for solutions to this equation, which are gamma invariant, they cannot blow up. We have compactness. And then, as Leon's showed us, one has many solutions. In particular, one has a least energy solution. So this problem has a solution which minimizes the Yamabe invariant, where now this Yamabe invariant is taken over functions in the Sobolev space, which are gamma invariant. Okay? So we may look for partitions which are gamma invariant, partitions by open sets which are gamma invariant. And this is, the definition is now very simple, because so now we look at a partition, at partitions of the Euclidean space where each one of these open sets is gamma invariant. And what is an optimal partition, a gamma invariant optimal partition for the Yamabe equation? Well, it's simply a collection of gamma invariant sets which are open, non-empty, pairwise disjoint, with the property that the sum of the Yamabe invariants for the sets minimizes the sum over all possible partitions. Because here now in this case, the first condition, which was the existence, this is guaranteed by Leon's theorem, because we have always existence. Okay, so now the idea is to look for this type of partitions. Okay, so we know that partitions without symmetries do not exist on the standard sphere, but maybe these partitions with symmetries do exist on the standard sphere. Okay, so okay, so let me look now, play the same game. So I am going to look now at the system, but I am going to be looking for solutions which are gamma invariant. So I look at the system on Rm. The lambdas, the coefficients of the interacting terms are negative, okay? And, and we are looking for solutions for groups like this, where k and n are larger than or equal to 2, so that every orbit has positive dimension, okay? So the questions are again, does the system have a minimizing solution? Do the components separate in space as the coefficients go to minus infinity? And then we want to see whether there is an optimal partition, and how does this optimal partition look like? Okay. Okay. So so now you see, since we have the symmetries, we have compactness, and then it is very easy to see that in fact the system has a fully non-trivial solution, which is minimal, has minimal energy. Okay. And in fact, it has infinitely many solutions, but in particular, it has a positive minimizing solution. And now we want to see how these solutions behave as the coefficients lambda go to minus infinity. So this we did with Alberto and Andre. How much time do I have, Lilian? I don't hear you.
Liliane?
Okay. Sorry, 9 minutes.
Okay. So we looked at this 9 minutes. Okay.
Maybe 10. Okay, I have 2 different times here. 10 minutes.
Okay. So indeed, I mean, we looked at the minimizer for. Okay. So we look at matrices, symmetric matrices, one for each k, whose entries go to -infinity, and we look at a positive minimizer for the system where the coefficients of the interacting term are the coefficients of the entries of the matrix, okay? And then what we prove is that the components of the solution converge strongly in the Sobolev space. They are continuous, and they minimize the Yamabe quotient on each one of these open sets given by, which are the sets where the U infinity is strictly positive. These are open sets because the function U infinity is continuous, okay? So this is the first statement. The second statement says that indeed this omega i's give us an optimal partition. Okay. So why is this true? So let me give you the main ideas. So the main ideas are, you see, here I have emphasized 2 words. One is the strong convergence, okay? And the other one is the regularity, the continuity. So the strong convergence is easy because since we have the symmetries, the embedding of the space of symmetric functions, of gamma invariant functions in L2 star is compact. And so this allows us to prove the strong convergence of the components of the solution. Now, the other part is, why are these U infinity i's continuous? Well, the reason is actually very simple in this case, you see, because if you take any function which is gamma invariant in the Sobolev space, this function is continuous almost everywhere. It is continuous except at the singular orbits, at the orbit which in this picture is the circle here and the line, the z-axis. And why is this true? The reason is very easy. The reason is, you see, let us look at the function u, which is gamma invariant. This means this function is constant on every orbit. So now let us look at the set of orbits, at the orbit space. So this is the space of orbits. The space of orbits is simply an interval, because you see, you have a homeomorphism which maps every orbit into a point here. And this homeomorphism is just given by taking the distance of the orbit to the z-axis. So you take the z-axis here, you take every orbit, and you take the distance of the orbit to the z-axis. So if the orbit is the unit circle sitting in the xy plane, then the distance is 1. If the orbit is the z-axis, then the distance is 0. And all other orbits are in between, okay? So this means that, well, we expect that the Sobolev space would be actually one-dimensional, okay? This is true except at the endpoints. One has to be careful at the endpoints because this is where the singular orbits sit. But if you take away from the endpoints, what you see is that indeed the norm in this space is equivalent to the Sobolev norm in H1. And then, since H1 consists of continuous functions, you will get this result, okay? So in this case, the regularity is easy due to the symmetry. So the symmetries simplify everything because really this is a one-dimensional problem, okay? So this proves the two statements, well, this gives the idea of the proof of the two statements that are given in this, here in the slide, but one can say more. One can say precisely how this partition looks like, okay? So let us see how this goes. So something that we have is that all of these guys, all of the omega, are smooth, are connected, they exhaust the whole space, okay? And we know precisely how they look like. So after reordering, the first member of the partition in the picture would be this green solid torus. The second one would be the domain between the yellow and the green torus. The next one would be the domain between the blue and the yellow torus. And the last one is unbounded, so that would be the exterior of the blue torus. Okay? So this is the decomposition. And you see, the nice thing about this is that, well, the boundary is just the product of all of this. That is the boundary is the product of these two spheres, so it is smooth. And moreover, one can see that they are ordered. So you have the first one, the second one, the third one, they are ordered. And this allows us to take these functions u infinity, so the limiting functions, and look at the alternating sum. So if you take the alternating sum, what you get is a gamma invariant sign changing solution for the Yamabe equation, which has precisely L nodal domains, okay? And this solution minimizes the Yamabe quotient over all solutions which are gamma invariant and have L nodal domains, okay? So let me make here some remarks. So the first remark is that Ding already in 86 showed the existence of infinitely many gamma invariant solutions for the Yamabe equation. And then recently, Fernandez and Petean showed that, in fact, there is a solution with precisely L nodal domains for the Yamabe equation on the sphere for every L, which is gamma invariant. And they did this using ODE methods, because as I just showed you, the problem is one-dimensional. So they used ODE methods to show the existence of a solution with precisely L nodal domains. So here we have an additional piece of information, which is that the solution that we obtain minimizes the Yamabe quotient over all solutions which are gamma invariant and have precisely L nodal domains. Okay? So now, I also want to mention that this result for two equations was proved previously by Angela and myself. And okay, so now let us go back to the problem of finding optimal partitions for a general manifold. So we go back to a general manifold, and then we had this result with Angela that I showed you at the beginning, that says, well, if you look at the Yamabe system, this Yamabe system has a least energy, fully non-trivial solution when the manifold is not locally conformally flat and the dimension is larger than or equal to 9, okay? So the question now is, what about the behavior of these minimizers when the lambda ij go to minus infinity? And the result that we have so far is the following one. If the manifold is not locally conformally flat, as in the previous theorem, but now we need that the dimension is larger than or equal to 11, then what we have is that we have again a good behavior. So the components converge strongly to a function u infinity, which is continuous. If you look at the domains omega I, where this function u infinity is strictly positive, they are open because this guy is continuous, and the function u infinity solves the Yamabe equation in omega I. Moreover, this collection is an optimal partition for the Yamabe equation, and well, in this case, one cannot order this partition in general as we had for the symmetric case that we considered previously. But if L is equal to 2, then we can consider the difference of the two components, and this gives us a least energy sign changing solution for the Yamabe equation on M. Now, I mean, we were expecting to have, to be able here to put the same assumption as in the existence theorem. So dimension larger than or equal to 9. But it seems this doesn't work. At least, I mean, we're still thinking about it. But these assumptions are needed, of course, to guarantee the strong convergence of the components. And also, we use it also to prove the regularity. But well, let me finish with some remarks. So, Aman and Humbert established the existence of a least energy sign changing solution under the same assumptions that we had in the previous theorem. This means when the manifold is not locally conformally flat and has dimension larger than or equal 11. So we were kind of expecting to have a better result, but so far we don't, okay? The other remark is that in general, an optimal L partition need not give rise to a sign changing solution. This is clear because I mean, there is not an ordering of the components of the partition. And well, that was all. Thank you.